in layman's terms. Coffee cup and a donut. Yes, yes. All right, oriented surfaces. See how that little, I should just take that out of my notes. That just wasted 5 minutes. An oriented surface is a two-sided surface in which the normal vector at every point on the surface exists, and such that the normal vector varies continuously over the surface. With surfaces like these, we can choose two possible orientations. So I think if you just look at this, there's a sphere, right? There's a sphere. We know that at every point on the sphere, there's a tangent plane, right? We did that last class. We have tangent planes at every point. If you have a tangent plane, you have two vectors. If you cross them, you get a normal, right? So at every point, there is a normal vector pointing off of this surface. As you move around the surface, those may change direction. They may get shorter, longer, but they vary continuously, which means they don't automatically, like all of a sudden go from here and then you move here and boom, and all of a sudden it's pointing inside. So that's what they mean by vary continuously. So we can look at all the normals pointing outward, which would be called positive orientation, or we could look at all the normals pointing inward. That would be negative orientation. But we can orient the surface, and any surface that we can do that on is called an oriented surface. All right? There are examples of surfaces which I won't get into that are not, you can't orient them. So how do we compute the normal vector of an oriented surface? Well, we've done this before. If the surface is given by a vector function, right? Then if we did the cross product of the partials, we did that on the sphere, cross product of those partials gave us a vector pointing out, which is what we use to find the equation of the plane. If we then divide that by its own length, it's a unit normal vector, isn't it? Yeah? If you take the negative of this vector, it's just going to point in the opposite direction. Okay? When your surface can be written as a function of two variables, x and y, so this is like a special case now, this cross product becomes this, and then the magnitude is this. So that should look familiar. This should look familiar to you. That's that was that shortcut formula we used a second ago? Square root of 1 plus partial of g with respect to x, partial of g with respect to y. Okay, but this right here, you would have to actually do the cross product to get that. With all that said, we now want to talk about a closed oriented surface. So if the surface is closed so that it encloses a solid E, so imagine you have a surface that actually closes itself off. A sphere is a great example of a closed surface. The solid in which it encloses we call E. Then positive orientation of the surface is the orientation where the normal vectors point away from the solid. So back on that sphere, the reason why we called positive orientation was because this sphere encloses a ball, right, a solid ball. Positive orientation is where your normals point away from the solid. Negative orientation, they point in towards the solid. We good? All right, and we finally have gotten to a surface integral of a vector field over a surface. So now we're going to be looking at that surface that's been sitting there for the last two classes, and imagine that it's sitting inside of a vector field. That vector field might be magnetic, it might be gravity, it might be electric. I thought I said electric. I did? Magnetic, electric, okay. It could just be, some flowing material, whatever. But it's now a vector field. Instead of a scalar function, we have a vector field. We will define, well, if we're given a vector field on an oriented surface, S, with unit normal vector n. What's unit normal vector n? That was that cross product of the partials divided by its own length. and the vector equation of the surface, if we know it, then this integral, notice the formula here, it's a double integral over the surface S of the vector field dotted ds. So you're actually integrating with respect to, it's not surface area anymore. Do y'all see that? This is not d capital S anymore. It's d vector S. What the hell does vector S mean? I'd like to try and explain what it means in the formulas that you see here. Because this right here is the d capital S. I'd like to try and come up with some meaning for that for you, all right? Here's my best attempt at trying to explain what it is and what this whole thing called flux is. Okay, and I'm going to use an oriented surface. I'm going to use a sphere as an example. This is an infinitesimal little patch on the sphere, right? I'm going to move this thing. Come on. I got to get this over here. At every point on this sphere, we have two vectors that we're looking at right now. So the point I'm looking at is this point right here. Man, those look like they're exactly the same. Let me get to the different points so you can see that these are different. Okay, there we go. I think that's a little better. So at this point, I have a green vector at that point, and I have a red vector. What do you think the red vector is? That's your normal vector, okay? That's your normal vector. It's oriented positively, so it's pointing outside of the solid, right? What do you think the green vector is?
It's the vector of the field.
That's the vector field, vector. Right? So remember, when you're in a vector field, at every point there's a vector, right? Has nothing to do with the sphere, right? So there you've got, at that point, the vector field vector, and you've got the red vector, which is your normal. What we'd like to do is, actually, you know what? The black, I should have said the black vector is your normal. I apologize. The black is your normal. The red, get the hell over here. I'm trying to get you to see what the red one is. Can you tell from that what the red one is? It's a projection. Okay, so I have to go back because I said the red one wrong. At that point, we have a normal vector, all right? And we have a vector field vector. If I do the projection of this green one onto this black one, I get the red vector, right? And what that red vector represents is, let's go back to water flowing, all right? If you're looking at that point, the water wants to flow in that direction, doesn't it? With a certain magnitude, a certain speed. If I project it onto here, this red vector tells me what the flow is in that direction. And the length of it is shortened now, right? Because it's been projected. So the flow in that direction is actually shorter than the flow in that direction. But all I'm interested in is the flow out of the surface. So that red vector represents that flow at that point. Does that make sense? So let's go back and look at this red patch. And let's imagine that we take a bunch of points. That's 4 points in that patch, right? Those are all normal vectors. Let me give you some more of them. There's a couple more. Those are all little normal vectors in that little patch. Let me show you all the vector field vectors that go with all of those. Okay, so those are all the green vectors that go with all those black normals. Let me project all those green ones onto those black ones, each one of them individually. And I get these red vectors. And I'm going to now take the normals and the vector field out. Those red vectors show you the flow out of that patch in the direction away from the surface, right? Like these things are running perpendicular to the surface. So this is somehow measuring how much is coming out of that patch. If it's magnetic field, electric field, gravity, whatever it is, it's a measurement of that flow, right? And if I add them all up, and I get a bunch and a bunch and a bunch and a bunch, right? Then I want to know like a measurement of all of this, right? And that's what flux is. It is a measurement of all these vectors coming out. Now I'd like to go to the formula. I was trying to get us to see what this was, right? And I was saying that that was ds. So it's hard to, well, boy, you're really not going to be able to see it from here. Maybe you'll just have to trust me. Maybe next class I can put it up here for you. You have to go back to your projection formula. How do you project a vector onto another vector? There's a formula for it, right? If you come in here and you start putting your field with the normal vectors, things will start to cancel out, and this is what you're left with. So you have to believe that from this is actually your field projected onto your normal vectors. That's what that computation is. And then what you're doing is you're adding them up over the surface, if that makes sense. But when you project a vector onto a vector, don't you get a vector? Right? So this piece right here has to be a vector, which is why we say D capital S, vector S. All right, I hope that kind of makes sense. All right, let's try and see if we can do one of these. Find the flux of the vector field capital F of XYZ equals YZX across the unit sphere. So they want flux, right? So here's what I want. Double integral over S of the vector field dotted with ds, which is double integral, and go back to the formula. I only pointed out one of the two formulas. The one I'm going to use mostly in here to begin this is this one right here, okay? We will use that one sometimes. So F dotted with R, partial of R with respect to U, cross partial of R with respect to V, dA, and this will be over D. Okay, R is the function that draws the surface. We've done this. This is a unit sphere, right? So what was R? Yeah, okay, let's go. Was it sine U cosine V? Sine U, sine V, cosine U. Wait a minute. Is that right? V is between 0 to 2 pi. See, the thing is, if you're using phi and theta, it's hard to get mixed up. But if you use U and V, it doesn't matter what you use. So you can do the whole thing and switch them all and switch your limits, and it's the same answer. So everyone is okay with that? Yep. All right, we did earlier the cross product. We did the magnitude of it, but see, this time we don't need the magnitude. So what is the cross product of those two? Okay, hold on. It's a vector, right? Cosine U. Right here?
Yeah, in the same vector.
Okay.
And then sine V, sine squared U.
Sine V, sine squared U. And then cosine U, sine U. Can I get a second on that? Anyone agree? Yes? Okay, good.
cosine of v sine squared u.
Oh, shit. Okay. See, this is where I knew we'd run into a problem. Hold on. Cosine v sine.
And then it was sine squared sine.
I don't know.
Yeah, I think it is B.
Where?
Cosine.
Where? This one?
I think it's B.
Cosine v?
Yeah.
Okay. Is that good? Okay.
Yeah, that's it.
I hope that's good. All right, we're not going to work that. We already did it. It's in your notes, right?
I mean, isn't it going to be wrong if it was?
Yeah, it will be wrong if it's not right. But do you want to go through and do the partials and cross them to be double sure? Okay. It's more really like this is just a method. Like what are we doing, right? Like what's the method here? So what we need to do now is we need to get the field and dot it with that vector. Dot products are easy to do, right? But what do we mean by the field? Well, here's your field. I need to dot that with this. But see, that has y, z, and x. This has u's and v's. We need it all in terms of u and v. So just like we did before, everywhere we see x, we replace with this. Where we see y, we replace this. And where we see z, we replace this. So this double integral right here becomes double integral over d. What is my vector field? It's y, which is
Sine squared.
sine v sine squared u. I'm going to run out of room. Let me just do it over here. Double integral d sine v sine squared u. Okay. Now z cosine u. Oh, hold on. Oh, why didn't anyone catch that? Hold on. Yeesh. That would have been a disaster right there. This is x. This is y. This is z. All right. Sorry, the cross product was just for that second part, right? Okay. So this is sine. That would have been not fun after that, huh? Sine u cosine v is x. Shit. It must be too close to the end of the semester. What is this first component? Y, right? Which is sine u sine v. Then z. What's z? Cosine u. Then x. Sine u cosine v. I want to dot that with, I don't ever want to see that again. Goodbye. This right here. So cosine v sine squared u, sine v sine squared u, and cosine u sine u, if that's correct, dA. Now we can replace dA with du dv, dv du, and do our limits of integration because we know our restrictions on u and v, but I need to dot that, so I may as well dot it now. And I'll write my limits here. How about 0, 2 pi, 0 pi. All right, dot products. This times this. Sine cubed u, sine v, cosine v, plus this and this, sine squared u, cosine u, sine v, and then the last one plus sine squared u, cosine u, cosine v. D du dv. And then you get the pleasure of integrating that. If it doesn't clean up, does it at all clean up? Oh, are those two the same? Ah, they're so close.
Whoa, the last two ones, they're the same thing, right?
Cosine and sine.
Oh,
V.
didn't see that. Shoot.
Yeah. That's life, man. Let's see if I have this one worked out. Give me just a second. Is unit sphere. Y, X, Z. Yeah, I don't have this one worked out. The book, example 4 in the book, they work out a problem very similar to this, but they use the vector field Z, Y, X instead. And, they get it to this point also. And once they get it here, they don't show much work either. You just kind of, but they show you what the answer is. You could do this now, right? I mean, given enough time, you could do that. I might go into three different integrals here. And in this first one, split my u's and my v's into 2 integrals and multiply them. And then in this one, split my u's and my v's and multiply them. Then over here, split my u's and v's and multiply them. Then just put them all together. All right, let's look at what's next. We have some special cases when we do flux. All right. There's nothing that says that when you compute the flux of something that the surface has to be closed. All right? Your surface does not have to be closed. If it's closed, then the orientation is easy to figure out, right? Like if I have the sphere, positive orientation is outward. But if I just give you like a sheet floating here in space, what's positive orientation? Right? So that's what these shortcuts are for. If I have that situation, would you agree that I could say z is some function of x and y? Right? If this is the ground down here, right? X, y, z. You've got some surface up there. Okay, if we have that, and our vector function has 3 components, p, q, and r, which, in the last problem, what was it was like y, z, x or something like that. Whatever those are, we're calling p, q, and r. This will become this, which we already knew, except we're using x and y here instead of u and v. And when you do this cross product, you will get this. Now this is kind of like, you remember we had the shortcuts where we had magnitude of the cross product? And it was square root of 1 plus partials and all that. This is that cross product before you square it. So if you do the cross product of these two, here's the shortcut. And look at this shortcut actually does the dot product for you. So what it will be is negative p times partial g with respect to x minus q times partial g with respect to y plus r. These are in your sheets that I gave you, right? What page is that on the sheets? Because this is a major thing to be able to reference.
Second to last sheet on that.
It's page 15?
Yeah. 14.
You have 14?
Mm-hmm.
Okay. Let me see what you have on here.
Yes, sir.
I only gave you one of those, huh?
Yeah, not all.
I didn't give you all of them. Okay, what I recommend you do is go to the notes I provided for this section online, because I have notes for all 3 special cases. All right? So it's this formula, and on the notes that I provide for you online, I know some of you I do not include this, so you might want to add this note in there. This is the formula, is if you're looking at your normals as pointing up out of the z-axis. It is?
Yeah, pointing up.
Okay, it's on the handout I give you. It's on the notes up there too?
Yeah, pointing up the.
Oh, wow, I did update it. What the heck? Okay. Is that the CDF or is that the PDF? Okay, the PDF version does not have it. Yeah, the CDF is good. So if you're using the PDF, make sure you add this note to it. So let's just try and back up and try and figure out what this is saying. If we're trying to find the flux through a surface, and we're looking at the normal vectors as pointing upward, right? And our surface is a function of x and y, and normals are pointing upward. Then this is all we have to do. The double integral over the region D, which would be the shadow on the ground of this computation with respect to area, and we're done. Now, what happens if the normals that you have are pointing out the bottom, which will be the case sometimes? How do you think this formula changes? All the signs change. This becomes plus, plus, minus, and that's it. All right? Now, if we have a special case where our surface can be written as a function of y and z, so this time your surface is out here like this, you know, and your shadow is going to lie onto the yz plane. Understand? This is our domain on the ground. Then x is a function of y and z. Then you don't have to go through all this mess of coming up with the formulas and crossing them. This is it right here. As long as you treat the normals as the ones pointed out towards you, okay, like out towards us. If you want to make your normals go into the page or towards the negative direction of the x-axis, then these will all change again. Negative, plus, plus. All right? And then finally, if your surface can be expressed as y equals a function of x and z, that's like this. Here's my surface this way. Then normals, which way? Out the right. Here's the formula. Is that what I have on my CDF? Out the right. I think on the PDF I don't say anything. And it's opposite on the PDF, isn't it? On the PDF version, doesn't say positive, negative, positive?
Yeah.
Yes? Okay, so if you're going to stick with the PDF version, that's your normals pointing out the left. This is what you have when the normals point out the right. Does this make sense or not? Use this formula right here if you want your normals pointing this way. If you want the normals to point out the left, switch the signs. That's what's in the PDF. I have 6 minutes. I think I have enough time to do one. At least set it up. Find the flux of the vector field. There's your vector field. This is, the surface is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above this region. So it's giving me this paraboloid. Okay, its region, if we look at it straight down, the region on the ground, right, is a rectangle. And that is a function of x and y, isn't it? So this is g of xy. This is p, what? Q, r, right there, right? And since it is a function of x and y, I can use a shortcut. It's telling me to use upward orientation for the normal vectors. So I want to imagine my normals are coming up here. So that means I can use the formula directly the way it appeared in the notes, which is this first one, right? I'm going to do double integral over d of negative p. Yeah, if the normals are pointing upward out the z-axis, right, upward, times partial g with respect to x minus q times partial g with respect to y plus r dA, which will be equal to double integral over d. What's negative p? Negative p. negative xy, times partial of g with respect to x. What's the partial of, I'm sorry, I'm a little off here. Here's my g. What's my partial of g with respect to x? What's that? Negative 2x. Okay. Now, negative q, what's negative q? Negative yz times partial of g with respect to y, negative 2y, and then plus r, plus zx. Got it? dA. Now, my region D on the ground is given to me by this restriction. So I knew that on the ground, xy, I was inside this box, right? That's D. So I'm going to have d what over here? dx dy or dy dx. It won't matter, right?
Do we plug in 4 minus x squared minus y squared?
Yeah, okay, so look, what we have to look at now is if I'm going to be integrating with respect to x and y, I need all these to be x's and y's in here, right? I have a z in here, but z is 4 minus x squared minus y squared, and that z right there is 4 minus x squared minus y squared. So I'm almost done setting it up. Integral 0 to 1, 0 to 1 of negative xy. I can actually put those together. What's that? 2x squared y. This one plus 2y squared z, but z is 4 minus x squared minus y squared. And then last one, plus x times 4 minus x squared minus y squared. dy dx. There it is.
This can happen.
This turns out to be 713 over 180. You would just distribute all this out, right? Multiply it all out, and then it's just pretty simple integration at that point. All right, so there's some more examples, of course, that I want to do. I'm not going to have time. I've got that one and that one. Now, just so you know, these two problems, example 5 and example 6, are actually out of your homework. They are problems